Demystifying Machine Learning, a Beginner's Guide. In the present-day context of technology, machine learning stands as a compelling and dynamic discipline that has garnered widespread attention and acclaim in recent years. This comprehensive guide seeks to serve as an illuminating beacon for beginners, facilitating their initiation into the captivating world of machine learning. At its core, machine learning represents a paradigm shift in computational problem-solving, where the emphasis shifts from explicit, rule-based programming to the cultivation of algorithms capable of autonomously discerning patterns and making data-driven decisions. Unlike traditional programming, where human developers explicitly code instructions for every possible scenario, machine learning algorithms are trained on data. Through exposure to diverse datasets, these algorithms uncover inherent patterns and develop the ability to generalize solutions for unseen situations. This adaptability is a hallmark distinguishing machine learning from traditional programming paradigms. The significance of machine learning in today's tech-driven world cannot be overstated. It fuels advancements in natural language processing, image recognition, recommendation systems, and more. Its applications span industries revolutionizing healthcare, finance, and autonomous vehicles. In a world awash with data, machine learning is the conduit through which actionable insights are extracted, enhancing decision-making, automating repetitive tasks, and fostering innovation. In essence, machine learning empowers computers to process data and learn from it, paving the way for unprecedented opportunities and efficiencies in our increasingly technology-dependent society. Machine learning encompasses a spectrum of approaches, each tailored to distinct objectives and data scenarios. Here, we elucidate the fundamental differences among the three primary types of machine learning. Number 1. Supervised learning involves training a machine learning model on labeled data, where each data point is associated with a known output or target. The model learns to make predictions based on input-output pairs provided during training. Supervised learning is guided by a clear objective, accurately predicting or classifying new, unseen data. It's akin to a teacher guiding a student. The model learns from labeled examples. A practical usage is email spam classification. An email spam filter is trained on labeled email data, spam or not spam. Number 2, unsupervised learning involves working with unlabeled data, where the algorithm seeks to uncover hidden patterns, structures, or relationships within the data. Unlike supervised learning, there are no predefined outputs. The algorithm explores the data's inherent structure. It's often used for tasks such as clustering and dimensionality reduction. An example would be customer segmentation. Supermarkets analyze customer purchase data to group customers into segments based on similar buying behaviors without knowing what these segments might be. Number 3, reinforcement learning is an interactive approach where an agent learns to make sequences of decisions to maximize a cumulative reward. It learns through trial and error by interacting with an environment. The agent takes actions in an environment and receives rewards or penalties based on those actions. It's widely used in robotics, gaming, for example AlphaGo, and autonomous systems. An example is autonomous driving. Self-driving cars use reinforcement learning to navigate and make driving decisions by learning from real-world experiences and optimizing for safe and efficient driving. In summary, these three types of machine learning cater to diverse scenarios and objectives. Supervised learning excels in prediction tasks with labeled data. Unsupervised learning uncovers patterns in unlabeled data, and reinforcement learning facilitates decision-making in interactive environments. Understanding their distinctions is pivotal in selecting the appropriate approach for a problem. Machine learning projects follow a systematic and iterative approach to harness the power of data for predictive and analytical purposes. The critical steps in this process are as follows. First, data collection is the foundational step in gathering relevant data to support the machine learning project's goals and objectives. It involves acquiring structured or unstructured data from various sources. High-quality data is essential for model accuracy and effectiveness. Datasets can be obtained from databases, APIs, sensors, or manual data entry. Second, data preprocessing encompasses cleaning, transformation, and feature engineering. It ensures that the data is in a suitable format for model training. handling missing values, scaling features, encoding categorical variables, and more. Clean and well pre-processed data enhances model performance. Third, model selection involves choosing the appropriate machine learning algorithm or architecture based on the project's objectives and the nature of the data. Consider factors like the type of problem, classification, regression, clustering, model complexity, and interpretability. Fourth, model training is the process of feeding the prepared data into the chosen algorithm to teach it to make predictions or classify data. The model learns patterns and relationships within the data during training using optimization techniques. Fifth, model evaluation assesses the model's performance using various metrics, for example, accuracy, precision, recall, F1 score, on a separate validation or test dataset. It gauges how well the model generalizes to new unseen data. Sixth, model tuning or hyperparameter optimization adjusts the model's parameters to enhance performance. Techniques like grid or random search help identify optimal hyperparameters. Seventh, deployment involves integrating the trained model into a real-world application or system for making predictions or decisions. Consider scalability, reliability, and monitoring in deployment. Eighth, continuous monitoring of model performance and retraining when necessary ensures that the model remains effective as data distributions change over time. It is important to note that models degrade over time, so periodic updates are vital. In summary, the machine learning process is a structured journey from data collection to model deployment, with continuous monitoring to ensure optimal performance. It empowers organizations to leverage data-driven insights and make informed decisions in various domains. Key machine learning algorithms are linear regression, decision trees, and k-means clustering. Use case of linear regression. It is used for predictive analysis when establishing a relationship between a dependent variable, target, and one or more independent variables, features. It's suitable for predicting house prices based on square footage, number of bedrooms, and location. How it works. Linear regression aims to find the best-fitting linear equation, a straight line in the case of simple linear regression, that represents the relationship between variables. It minimizes the sum of squared differences between predicted and actual values. Decision trees are versatile and employed for classification and regression tasks. They are helpful for scenarios like credit risk assessment, classification, or predicting sales, regression. Decision trees make decisions by recursively splitting the data into subsets based on the most significant attribute at each step. The goal is to create a tree-like structure where each leaf node represents a class or a predicted value. K-means clustering is unsupervised learning used for data segmentation. It's applied in customer segmentation for marketing strategies, image compression, and anomaly detection. How it works. K-means divides data into K clusters based on similarity. Initially, K centroids are placed randomly. Data points are assigned to the nearest centroid, and centroids are recalculated. This process iterates until convergence, optimizing cluster formation. These fundamental algorithms lay the groundwork for various machine learning applications. Linear regression is for prediction, decision trees handle classification and regression, and k-means clustering groups data into clusters based on similarity. Understanding their use cases and workings is pivotal for aspiring data scientists and machine learning practitioners. Demystifying jargon is essential. Overfitting happens when a machine learning model learns the training data so well that it becomes too specialized. Imagine a student memorizing exam questions without understanding the concepts. When new, unseen data is introduced, the overfit model struggles because it can't be generalized. Like a student taking practice exams but failing in real-life scenarios. Underfitting occurs when a model is too simple to capture the data's complexity. Think of a student who needs to study more. They perform poorly in practice exams and real-life situations, similar to a student guessing answers randomly. Accuracy measures how many predictions a model gets from all predictions. For instance, if a model correctly identifies 90 out of 100 objects, it has 90% accuracy. It's like getting 9 out of 10 questions correct on a quiz. Precision emphasizes the accuracy of optimistic predictions. It answers, of the items predicted as positive, how many are positive? It's crucial in scenarios where false positives are costly. Imagine a metal detector that rarely beeps falsely. These explanations aim to simplify complex machine learning terms, making them more approachable for newcomers to the field. Overfitting is akin to memorization. Underfitting is like not studying enough. Accuracy quantifies correctness, and precision focuses on avoiding false positives. Here, we have tried to present machine learning to encourage beginners. Follow us on our channel, like and subscribe. That will help our channel to produce more videos like this. We welcome suggestions. Please let us know what is your area of interest and we will help. And if there is enough to justify, we may make a video.